So a brief introduction to the Simons Institute. So we are the leading international venue for collaborative research in theory of computing and related fields. The institute was established in 2012 with a very generous grant from the Simons Foundation, which continues to support us in significant ways. And the institute brings together world's leading researchers in the theory of computing and related fields, as well as the next generation of outstanding young scholars. And our main mode of program activities is each semester we have two programs, two thematic programs, and that attract several long-term visitors, both senior and junior to Berkeley, and which also include multiple workshops that convene more short-term visitors on for week-long workshops. And so this week is one such workshop. I'd like to welcome you to the workshop on probabilistic circuits and logic, the second workshop as part of the program on logic and algorithms in database theory and AI. And first, I would like to thank the organizers of this week's workshop for their hard work in putting together a great program. And they are, so if you're here, just raise your hand or stand up. Guy van der Broek, who's the chair of the workshop, Dennis Deratani-Mowa, and Stefan Mengel. Okay, so, thanks for the organization. So let's give them a round of applause. And before I hand it over to the organizers for the information about the scientific content of the workshop, just a few logistics for the coming week. So we have food before the first talk and during the breaks, just outside the auditorium. And for lunch, you're on your own, but there are many excellent choices in walking distance. And one sincere request we make is that you please leave any food and drinks outside the auditorium. Bottled water is fine, but anything else, please leave it outside. It helps us keep the auditorium clean, as you see. And if you want to leave some stuff during lunch or other times, there are lockers on the other side of the corridor, and then you can it's a good place to leave your stuff. And any AV issues, our videographer Omiyad Far is here to help you. And as always, all the talks are recorded and stored, archived in our YouTube channel, and also live streamed, so they have a long life and impact beyond this week. And so one other thing is that if you're for any of you who might be active on social media, like Twitter X, so if you consider live tweeting from the workshop, if you do that, tag us at Simons Institute, and we'll be sure to post comments. And finally, a special thanks to the events team, specifically Ashley Hassan of the events team and Frida Orr, who helps for managing all the logistics for this week's event. And they will also, and DA and other staff will be on hand to answer any questions. So with that, I'll hand it over to Guy, who will say a few words about the workshop.
Hi, everyone. So also on behalf of Stefan and Dennis and myself, welcome. So this is a workshop on probabilistic and logical circuits. And I think the reason why I was excited to kind of bring this group together is because there's really several sub-communities here that really don't know each other. And I thought maybe it would be useful for the start of this program that I kind of try to map the community for you, and then we can actually get into the technical talks. And so what we try to do here is bring together, of course, the database folks that have been here also for the logic program for a while. And so they've been looking at circuits also for at least 15 years in the context of probabilistic databases, enumeration of solutions to queries, explanations. And so they have a very deep knowledge about the theory of logical circuits. At the same time, we have here several people from the machine learning community who really look at circuits as statistical models, as generative models or deep generative models, people that come from the sum product network, GutSet community. And so they think of these as statistical models, not necessarily logical ones. But in the end, there's so many commonalities that I think it would be very useful that we talk to each other. And then maybe there's several more communities here. There's, of course, the classical AI community that thinks of probability distributions as being graphical models. And then for them, circuits and things like and/or graphs are ways of essentially thinking of how to reason about graphical models. And so that, of course, connects to the graph community. And then we also have many representatives here of the model counting and approximate sampling communities. And so they don't think of the world as being all about circuits necessarily, but they care about the very related problem of counting solutions, counting things. And so I hope we'll find many common interests here, and we'll hopefully have talks kind of spread throughout these communities where we can learn from each other how people kind of perceive these problems. And with that, I would like to invite Dan to start the first talk on circuits for query provenance.
Okay, thank you, Guy. And I need to apologize. Apparently, I mixed up the talk title. It's not the one that is posted, but it's the same content, so don't worry. I just try to make it as attractive as possible. And I should also mention this is joint work with Paul Beam, Nilesh Talvi, Abhay Jha, Jerry Lee, and Sudeepa Roy, and Sudeepa sits right here. Okay, so take your favorite problem on Boolean formulas F. This can be satisfiability, can be model counting, can be constructing a binary decision diagram, a particular kind of a circuit, whatever problem you can think of. So now, in general, this problem is exponential in the size of the formula. But now assume that your formula is actually the provenance, or also called the lineage or the grounding, of a first-order sentence queue. And the only input is the domain over which you do this, over which you compute this provenance. So the question now gets more refined for a fixed sentence queue. The question is, what is the complexity of your problem, whatever your problem was, as a function of the size of the input for this fixed sentence queue? This is the problem I'm going to discuss today. So to make it a little bit more refined, F will be the provenance of some fixed first-order sentence, and all the results that I will mention, they will restrict the what kind of first-order sentences we are considering. And then I'm going to discuss two problems. One is a complexity of the weighted model counting problem for the Boolean formula F. And more interestingly, I'm going to discuss the size of some binary decision diagrams, ordered binary decision diagrams, free binary decision diagrams, and Decision-DNNFs for this Boolean formula F. My main goal is the second bullet, but the weighted model counting is a great warm-up and also establishes some of the terminology. A glaring omission is the satisfiability problem, just because nobody apparently has looked at this particular the dimension of the satisfiability. The main message of this talk is that we can go from logic, from syntactic analysis of the logical set of the sentence in first-order logic, to algorithm and complexity results for the grounding or the provenance of the Boolean formula resulting from that sentence. And throughout this talk, I'm going to describe some concrete results, but my main goal is to get you excited about the problem itself, not about the results, because I think there are many new problems that have not been addressed, and I hope somebody will actually address them. Okay, so with this in mind, let's start directly with weighted model counting. This is a classical problem given a Boolean formula F. The model count for F, denoted sharp F, is a number of satisfying assignments of F. It was proven in a classical paper by Variant in '79, actually two accompanying papers, that this problem is sharply complete, even if F is restricted to a 2CNF, to a positive 2CNF formula, or a positive 2DNF formula. But I'm going to discuss a slight generalization of this problem, where every Boolean variable is associated with a probability, Pi, for that Boolean variable, which is a number between 0 and 1. And the goal is to compute the probability that the formula is true. And for reasons I'm not going to get into, this is often called the weighted model count for F. And the problem is a weighted model counting for F. So why do we consider the slightly more general problem? Because it has an important property that we need. Namely, it is weighted model counting can only become easier for subfunctions. A subfunction consists of taking your original function f and applying some partial substitution. In other words, we set to 0 or 1 some variables of our choice, and we get a smaller formula. And obviously, if we have an algorithm for computing the probability of the original formula, we can always answer this subfunction by simply specializing those probabilities to 0 or 1. We are actually going to use it in reverse. If the sub function is hard, this implies that the original formula was hard as well. Okay, so how do people do weighted model counting? There are essentially only two things you can do. One is a Shannon expansion. This is what all the solvers are doing. Shannon expansion says, pick a variable xi, compute the probability of the subfunction when xi is set to 0, of the subfunction when xi is set to 1, and then combine them in the right way to get the probability of f. Of course, you need to recurse, so this typically leads to an exponential time algorithm. The second formula is if you are lucky, and if your Boolean formula is a conjunction of two formulas that do not share variables, then the probability is their product, and this makes much more progress than the Shannon expansion. Okay, so what are the Boolean formulas for which we want to do weighted model counting? They are the provenance, or the lineage, or the grounding of a first-order sentence. So fix a first-order sentence Q over some relational vocabulary. The provenance of Q over a domain size n, this is the only input, a domain size n, is the following Boolean function defined inductively on Q. If Q is universally quantified, then simply substitute the logical variable x with every value in the domain, takes a conjunction. If Q is a conjunction, keep a conjunction. If we had an existential quantifier or a disjunction here, we know what to do. We put disjunctions. Negation, just push the negation through the provenance expression. When we finally reach atoms, the atoms are already grounded. They have constants on all the positions. And then their provenance is a Boolean variable uniquely associated to this grounded atom. Okay, this is a provenance, or the grounding, or the lineage of a first-order sentence for a fixed domain size n. A quick example. Here is a universally quantified first-order sentence, and its provenance over a domain size n is a big conjunction with n squared clauses, and yeah, it's pretty easy to read. So with this definition, here is a problem that we are going to study. Given a first-order sentence Q, what is the complexity of weighted model counting of the grounding of Q as a function of n, as a function of the domain size? So the results, all the results in this talk will be restricted to a pretty important, and I should say severe restriction of first-order logic. We do not handle negations, and we have a single type of quantifier, only existential quantifiers or only universal quantifiers. Of course, nothing prevents you from considering the problem more general, but I don't have any results to show you there. Yes, Michael?
So then just to clarify, the input of the paren is the n, and also the probabilities for each variables, right? Or...
The input is indeed n, and for the weighted model counting problem, also the probabilities of all the variables. That's correct.
And so you have a family of decision problems, one for every Q, right?
So there is very nice observation. Thanks, Bokyon. There is a family of counting problems, one for each different Q. Lots to study. Each Q a different paper. That's how we should think about this. Okay. Yes.
Are you assuming some independence of when you define these probabilities, or they are the marginals of a joint probability?
Right, this is an important question. So throughout the model counting problem, we assume that these variables are set independently to 0 or 1. And the difficulty comes from the Boolean function itself, not from the correlation. There are ways to model correlations in this setting. Guy and I, we have a survey paper in Foundations and Trends, and there we discuss how to model correlation in this setting. Okay, good. So these are the definitions. So let me show you the first syntactic feature that we need to pay attention to in that sentence in order to understand the complexity of the grounded formula. And that is a hierarchy of variables. Fix a sentence Q, first order sentence Q, and for each logical variable, let's denote at of x, the atoms the set of atoms where the variable x occurs. We call a sentence or a query hierarchical if for any two variables, the set of atoms where they occur form a hierarchy. Either one is contained in the other, or they are disjoint. They are not allowed to overlap. And then we call the query hierarchical. And it's not easy, it's not hard to prove, it's actually very easy, that if you restrict your sentence to just conjunctive queries without self-joins, it's a very restricted class, so no self-joins and conjunctive queries, then we have quickly a dichotomy. If the query is hierarchical, then the weighted model counting is in PTIME, otherwise it is sharply hard. And this is immediate to see if you look at two examples. Here is a hierarchical conjunctive query. It's hierarchical because X occurs in both atoms, Y occurs only in S, and they are contained in each other. And with a little bit of thinking, you can figure out that you can compute the probability of its lineage, of its provenance in polynomial time. Yes, Ahmed.
If we have free variables in the query, how do we define the hierarchical property?
Okay, good question. So this example only has two variables. The definition of hierarchical also applies to to higher arities. You just need to check this for every pair of variables, and the queries become bigger, I should say. But the definition still applies. Here is an example of a non-hierarchical query where X occurs in R and S, Y occurs in S and T. They overlap, none contains the other. And for this reason, the query is sharply hard. If you read my little footnote, the way to prove sharply hardness is to prove that a subfunction is actually one of the known classes to be sharply hard. Yes?
What type of reduction you are using?
For the hardness proof? Yes. Just a subfunction.
But it's like, it's tuning, it's...
So in this case, it is it's a many one reduction. But for the big results that I'm going to show in the next slide, we have a much more complicated reduction, which is that is a Karp reduction. Okay, so we have a little dichotomy, but it's for a very restricted class of queries, only conjunctive queries without self-joins. What happens if we allow self-joins? What happens if we move on to the entire class of union of conjunctive queries? And the good news is that we have a much more difficult dichotomy theorem here as well. For any query Q, which is a union of conjunctive queries, or a dual universally quantified, the weighted model counting is either in polynomial time, or it is sharply hard. And I should mention that the algorithm that gives us a polynomial time case is elegant and simple. The hardness proof is very difficult. And that is indeed, it's not a many one reduction. It is a much more difficult proof. Good. This was a good news. So we have this dichotomy. Now, what is the syntactic feature that determines this dichotomy? And I'm not going to show this to you in full. But I'm going to point out that hierarchy is not the one. Hierarchy is a necessary condition for tractability, but it is not a sufficient condition. And here is a query, we will come back to it, which is hierarchical. It consists of two conjunctive queries. It is a union of two conjunctive queries. Both are hierarchical, yet it turns out that this query is sharply hard for weighted model counting. The dual is a universally quantified collection of clauses, and it's also sharply hard. Okay, so this is all I wanted to say about weighted model counting. The main takeaway is that we can go from static analysis of the query to decide the complexity of the weighted model counting problem. Yes?
That paper with a beautiful dichotomy, you did not know the complexity of the meta problem, deciding which. Do you know more now?
Right. So given Q, what is the complexity of deciding whether we are here or here? It is still open.
What's the upper bound? Do you remember?
It's something exponential, but you need to alternate a bit from CNF to DNF or vice versa once for every quantifier. And I don't know if this increases the number of exponentials or not. Nobody has looked deeper into this. This is why I'm looking at this audience. Maybe somebody will clarify the query complexity of the decision problem. Okay, good. So the main takeaway from this part and from the entire talk is that we can go from first order logic, from a static analysis, to understanding the complexity and getting to the algorithm of the corresponding problem. I should mention that Antoine Amarilli and Ceylan, they have a beautiful paper where they extend this dichotomy to a much richer language that includes data log. It's mostly a negative result. They say that there are no new tractable queries. What you get in UCQs, that's it. Beyond a union of conjunctive queries, it's open. Adding negations or quantified alternations leaves open the dichotomy. I should also mention that this result is orthogonal to a well-known dichotomy theorem for the counting problem of satisfiability by Crenu and Herman. They classified the counting problem into polynomial time or Sharpe-Hard based on the type of clauses. If all the clauses are affine, then the problem is in polynomial time. Otherwise, it is Sharpe-Hard. This is not what we are doing. We are our classification is based on the type of Boolean functions. Okay, so with this in mind, my next topic is to talk about binary decision diagrams. And for this, I need a quick background into binary decision diagrams. A wonderful book is this one by Ingo Wegner, which I brought here. He explains that the research on binary decision diagrams gets back to the 50s. It's a wonderful book to read. In this talk, I'm going to focus on 3 types of binary decision diagrams: free binary decision diagrams, order binary decision diagrams, and Decision-DNNFs. The first one are the same as read-once branching programs, subject to the read-once rule. This is why they're called read-once. Some people might know them under this name. Okay, so here is how they look, how the FBDDs look like. A free binary decision diagram is a DAG, a rooted DAG, where every internal node is labeled with a Boolean variable and has 2 outgoing edges, one labeled 0 and the other labeled 1. And the leaves, they are labeled 0 or 1. They represent naturally a Boolean function, which you can easily see by inspecting the FBDD from the root. You read the variable x. If it's 0, you go left. You read y. If it's 1, you go right. If u is 1, you go right. And now you know the function is 1. And this, by the way, corresponds to this min term of the Boolean function, not x, y, u. There is one single restriction, the read once property. On any path from the root to the leaf, each variable can be read only once. It's an important restriction. Ordered binary decision diagrams, they further restrict FBDDs to a fixed variable order. On any path, we need to read the variables in the same order. This is not an OBDD because here we read them in the order XYZ. Here we read them in the order XZY. But OBDDs make them easier to synthesize. Every Boolean function has an exponential size OBDD, just a full binary, full decision tree. But what we want a more compact circuit, and FBDDs can be exponentially more compact than OBDDs. As a quest for even more compact circuits, the Decision-DNNFs, they extend FBDDs with end nodes that have to be decomposable end nodes, which means that the variables on the left descendant should be disjoint from the variables on the right descendant. It turns out that they are a little bit more compact, but not by much, by only a quasi-polynomial amount. We proved that every Decision-DNNF can be converted into an FBDD, which is only slightly larger. Okay, so there are 2 important properties that we need from these circuits, and they are 2 of the about a dozen or so properties mentioned by Wegner in his book. The first property is that we can do weighted model counting in linear time in the size of the circuit. This is easily seen because each node in an FBDD is essentially a Shannon expansion. So we can do weighted model counting in linear time. And the second, very easy to see, it says they are closed under subfunctions. If I want to set y to 0, I simply remove this node and rewire the incoming edges. I need to do the same thing here. And I get a FBDD which is not bigger. It can even be smaller. Okay, so these are the binary decision diagrams. And my goal is to compile a Boolean function into a BDD. This idea of compiling knowledge was introduced in an influential paper by Darwiche and Marquis in 2002. And we elevated this to what we call query compilation, which compiles the provenance of a fixed query Q as a function of n. I should mention query compilation turns out to be a poorly chosen term because query compilation is a very serious problem now in database systems. Database systems, they need to compile to machine code, and this is a major challenge because it can't take too much time. But it's a completely different problem from our query compilation, which is a pure theoretical study. Good. So I still have, I think, 15 minutes, right? So we still have time to go over the core of this talk, namely how to compile from first-order logic all the way to circuits. And I'm going to start with OBDDs. Ordered binary decision diagrams. Again, they are FBDDs, where we have a fixed variable order, usually denoted by. There is a fixed variable order that all the paths need to traverse. They turn out to be quite similar to DFAs, and this helps a lot in synthesizing them. Synthesis is a fundamental property that the OBDDs have and the FBDDs do not have, and it's the following property. If we have two OBDDs, G1, G2, for two Boolean functions, F1, F2, and these two OBDDs, they use the same variable order, then we can synthesize an OBDD for the conjunction or disjunction, and this new OBDD is like a product automaton. It's no bigger than the product of the two graphs. Okay, so the question that I'm going to ask is, given a UCQ or a dual UCQ, what is the size of the OBDD as a function of n? So let me give you some intuition how we can get efficiently from queries to OBDDs. Here is one of the queries that we considered. I took the dual of that hierarchical query. And to give you some intuition, this is grounding or is provenance for a domain of size 2. Yes?
Clarification, by the size you mean the optimal size, the smallest OBDD.
I mean the optimal size, correct. In this simple example, what happens if you look at the hierarchy of the variables, remember that syntactic criteria, we observe that X occurs more in more atoms than Y, so it makes sense to choose a variable order on the groundings of S that traverse S in row major order. And this is what I did here. So we inspect R1 first, and if it's 0, then we need to expect everything in that first row. And then we inspect R2, and then everything in the second row, and so on. The OBDD has size n. And synthesis allows us to construct more complicated OBDDs for more complicated sentences. Here is a second sentence. It's almost identical to the first one, but we have T instead of R. Importantly, the hierarchy of the variables is the same. This also wants to traverse S in row major order. And we get a similar OBDD with the same variable order for S. Both traverse S in row major order. So now we can compute an OBDD for the conjunction, a much more complicated query, the conjunction of these two. And it turns out the size is not even quadratic. If you work it out a little bit, it's only linear in n. So these OBDDs can be very, very efficient. Of course, this basic construction doesn't work all the time. Here is when it fails. First of all, it fails if the query is non-hierarchical. This is a dual of the RST query we saw earlier. Here, S would like to be traversed in row major order in order to match R, but it would like to be traversed in column major order to match T. And it's not obvious that we have a good traversal. But it gets more subtle than this. Before I show you the next queries, I want to drop quantifiers because they clutter the slides. So look at those quantifiers, they are gone. Okay, so no more quantifiers. So here is my second query where the quantifiers are dropped, but they should be there. This is a hierarchical query. The first clause is hierarchical, so is the second. But the first clause wants to traverse S1 in row major order. The second clause wants to traverse S1 in column major order. There is a conflict, and it's not clear if we ever have a good order traversal. It gets even more weird. You can stretch it even further. S1 wants to be traversed in row major order, but S1 and S2 must be traversed in the same order because of the second clause. And S2 insists on being traversed in column major order. You see the conflict. Continuing like this, for every k, you can construct a query that has k plus 1 clauses that has this conflict between the leftmost clause and the rightmost clause. Yes, Remy.
So in canonical query, we usually have exponentials. So here we always have for alls. So what is for all mean? Is it for CQ?
Right. So I should have emphasized this. So the question is, what about the existentialists that now became universals? For every query, the weighted model counting problem or the circuit computation problem is the same as for its dual. The dual is obtained by replacing exist with for all, replacing and with or, and replacing or with and. And if you have negation, then you keep negation as well. This is a dual. So this universally quantified query, if you take the dual, universal quantifiers, they become existentials, or becomes and this is indeed our RST query. Similarly, you can play the same game with each of these HK queries and get a union of conjunctive queries by taking the dual. I find it more convenient actually to use a universally quantified expression. This is why I chose them. So the takeaway here is that all these queries, they don't seem to have a good variable order. And indeed, what we proved is that the lineage expressions for each of these HK has OBDDs which are provably exponentially large in n, in the domain size. Notice this is a result that applies to FBDDs beyond OBDDs. So it's a stronger result. It's kind of expected. And by the way, Decision-DNNFs, they are not much better because they are only quasi-polynomially more efficient than FBDDs. Okay, so with this result in mind, we can examine the second syntactic feature that helps us understand the complexity of query compilation, which are inversions. And inversions are just the elevating the phenomenon you saw on the previous slide to a general query. An inversion is a sequence of atoms that essentially says you don't have a good variable order. In the first atom, you have two variables, x and y. X occurs in strictly more atoms than y. In the last atom, y occurs in strictly more atoms than x. And in between, they insist that they will be traversed in the same order, and that gives us a conflict. So here is an example. These four atoms here, they form an inversion of length. This is a 2 inversion in H2. Okay, so this is a second syntactic feature that we are going to examine. And it turns out that this is necessary and sufficient to decide whether your provenance has polynomial size OBDDs. If Q has no inversions, then its provenance has an OBDD, which is essentially linear. It's linear in the number of ground atoms. And if the query has an inversion, then its OBDD is exponentially large. At this point, yes.
The second lower bound is an unconditional or is conditional lower bound?
The second one is unconditioned. I think one thing to worry about is I stated the lower bound for the HK queries as lower bounds for FBDDs, but here I only stated for OBDDs. And this is not an accident. The way we prove this lower bound is through a reduction that involves synthesis. Here is how the proof goes. Imagine that you have an OBDD for the provenance of Q. Then what we can do, we can create k plus 1 subfunctions, one for each clause of HK, by specializing all the unwanted Boolean functions. So from one OBDD, we have k plus 1 OBDDs, one for each clause of HK. And we are in good shape because all these OBDDs, they use the same variable order. So now we can synthesize them to get an OBDD for HK, which we know has to be big. And this is what gives us the exponential lower bound for the size of an OBDD. Yes?
Before, in the previous slide, you showed us these hierarchical queries for which synthesis is not possible. But these queries were easy for model counting by what you told us before. So what is the point? Just that synthesis fails even for easy counting queries? Is that?
Yeah, Fokyon is one slide ahead of me. This is exactly the question I'm after. Some queries, they turn out to be easy for weighted model counting. However, there are no polynomial size OBDDs for these queries. But I should mention that the HK queries, all these queries are Sharpie hard. However, the statement that Fokyon alluded to still holds, and I want to get there, and I still have 6 minutes to get there. Okay, so we have a very simple dichotomy for OBDDs. If the query has an inversion, forget it. The OBDDs are exponentially large. If the query doesn't have an inversion, it's fantastic. The OBDD is essentially linear in the size of the number of ground atoms, which is n to the arity of the largest arity of your schema. Okay, good. So this is Fokyon's question. Is it sufficient? Are all queries that have a polynomial time OBDD, are these all the queries for which we can compute weighted model counting in polynomial time? And the answer is no, because for weighted model counting, we use a technique which we don't know how to transfer to circuits, and that is inclusion-exclusion. Here is a query for which inclusion-exclusion works beautifully. There is, it looks like H1. We have this inversion from the first clause to the second clause, but there is a third clause here. And remember, everything here is universally quantified. And because of that, the only way this last clause can be true is if Rx is true for every x, or T of y is true for every y. So we can separate these two universal quantifiers, then we can distribute. We can simplify a little bit these two CNF expressions, and we get our first order sentence as a disjunction of two conjunctions. Why is this good? Because now the probability, we can express it as an inclusion-exclusion formula. Probability of the first conjunct plus the probability of the second minus the probability of both together. And the last expression simplifies again, and we end up with 3 expressions. All of them are inversion-free, and therefore we can compute their probabilities in polynomial time. The takeaway is that we can compute the probability of QV in polynomial time. However, its OBDD is provably exponentially large. Yes, Kuldeep.
But what about DNNF? Do we know something about?
We know something about DNNFs. I'm not going to talk about it. That's going to be the next talk. Okay. So again, my message is from static analysis of Q, we can get to judgments about the optimal size of the OBDD for its provenance. But the second message is what Foucault observed. OBDDs are essentially incomplete. They do not capture everything we know how to compute in polynomial time. I should also mention that Paul Beam and Vincent Liu, they showed that a similar theorem also holds for SDDs, a strictly more powerful class of circuits than OBDDs. So the interesting question is, how do we make this class of circuits complete? Are the FBDDs complete? So this is going to be the last topic of my talk, and I think I can finish it in two minutes. So FBDDs and Decision-DNNFs. By completeness, I mean that if we can compute, do weighted model counting in polynomial time, it is a case that the lineage has an efficient circuit. In this case, we're looking for an efficient FBDD. This is a question to address. And the answer is no. Both of them are incomplete, and I'm going to show you why. In order to give you the example for which they are incomplete, I need to start from H3, which had 4 clauses. They're all universally quantified, Remy. So yeah, not existential. They're universally quantified because I've chosen to be conjunctions of disjunctions as opposed to vice versa. And I'm going to take these clauses, 4 clauses, and arrange them in a different way. It's going to be a very small DNF formula that you can see here. It's not super important that we look at the details. What we proved is that the probability of this new query called QW can be computed in polynomial time. However, every FBDD or Decision-DNNF is exponentially large. How do we compute this probability in polynomial time? Well, we know what to do. We apply the inclusion-exclusion formula. But there is a problem here. By the time we reach the conjunction of all these terms, we get a conjunction of all these 4 clauses. Some of them are repeated here. But this is exactly H3, for which we cannot compute the probability. But it turns out that because of the shape of this formula, these 2 terms, which are both hard, they cancel out. And since they cancel out, we are left with only terms that no longer have an inversion. At least 1 clause is missing from each of these terms. And it turns out that this query, we can do weighted model counting in polynomial time. I have here 1 line about the proof, which is very subtle and kind of long. It had a cool idea there, but I'm going to skip it because I am running out of time. Good. So quick takeaway from this part. Both FBDDs and Decision-DNNFs are incomplete. I should mention that the theorem I mentioned has a slight generalization from QW to a slightly larger class of formulas. But we still don't know exactly which sentences admit a polynomial time FBDD or Decision-DNNF. The other thing to take away is how powerful inclusion-exclusion is with cancellation. This turns out to give us a lot of power for computing the weighted model, for doing weighted model counting. Good. So quick summary. The main takeaway I'd like you to get from this talk is how to get from logic to algorithm. Through static analysis of the first order sentence, we can draw conclusions about the complexity of a Boolean formula obtained by instantiating Q over a domain of size n. And the syntactic features that we discussed are the hierarchy, the inversions, and a much more complicated one to see, which are those cancellations. And they're related to a Möbius function that Mikhail will hopefully talk about. Lots of open problems, and I hope to get some of you excited about them. What about going beyond UCQs and their duals, like adding quantifiers or negations? Don't try to add recursion. That's done. Antoine has done this, and it doesn't work. We don't. I mean, if you solved it, and the answer is no, you don't get any new tractable queries. What about a dichotomy for the full first order logic? Interesting. If we have such a dichotomy, we will not be able to decide between the hard and the easy queries by Trachtenbrot's result. That would be a very interesting dichotomy, completely different from the one we have. What about satisfiability? Nobody has looked at this. You have an arbitrary first order sentence. You look at the groundings. What about the satisfiability of all the sub-functions that you can get from that grounding? I think it's a very interesting problem to study. I have no idea how to approach it. And the big question for this morning is there a complete family of circuits for unions of conjunctive queries? And Mikhail will look into this. And on this note, I will stop here, say thank you, and sorry for running over 3 minutes.
I think we have time for a question or two.
Can I ask questions directly, or is there a microphone?
He's a boss.
Thanks. This thing. Yeah, I just wanted to check I correctly understand this question about SAT, because I think it's interesting. So then your open question about SAT, is it you fix a formula, say in first order logic, and you want to know if given a database there is a sub-database that satisfies the formula?
I would say given a domain size n,
yeah,
you ground it, you get a single grounding, and now I would examine all the sub-formulas, which is essentially choosing your database.
So then these sub-formulas, they're not given as input? I'm not sure.
Well, you want all of them to be decided by the polynomial time, or to prove that the entire class is in the computer. You can formulate your problem as you want.
Okay, thanks.
Definitions are easy. Hard results
are hard, yeah.
Maybe just a super quick question. Most of your results are with respect to...
Turn it off again.
Your results are with respect to n, the size. What is the asymptotic complexity, or it depends on... so for very large n, what happens to the...
so for very large, and so the data has a very simple analysis. The total number of Boolean functions is 2 to the n, and you see how many OBDDs you can, or FBDDs you can construct with this size. It turns out that on average you need exponential size circuits to represent all the Boolean functions. So only a small fraction will have a polynomial size circuit, but it doesn't go beyond exponential. Exponential is enough.
Thank you.
Yes.
So you said that is it always? I don't think it works. Is it always the case that when the size is polynomial, then generating it, maybe synthesizing it, is a polynomial process?
So this is a very nice observation. Thanks, Dina. So it could be the case, in principle, that the size of the BDD is small, but it's difficult to synthesize. However, we did not encounter this. In all examples that we know, whenever the size is small, we also know how to synthesize this efficiently. But it is a question.
If the problem is not satisfied, or the size is zero, then recognizing it.
Exactly. You can even think of an undecidable problem in n. Just have a 0-1 circuit, very simple, but you can't synthesize it.
All right, thanks again.